In this lecture, we will revisit the Colpitts oscillator and analyze it using the negative resistance model. But this time, we will also include the loss of the inductor. We have already seen the Colpitts oscillator. So we have this inductor and we are going to include the loss of this inductor by this resistor R. And we will analyze this for assumption CGS is equal to 0, which says that operating frequency is much small compared with the threshold frequency. And second, we will include the channel length modulation. So we had already used these two assumptions for the last lecture analysis. Now in the negative resistance model, we have to basically divide the whole circuit into two impedances. Like this. So first we are going to call Z in and this as ZL. And we know that negative R model implies that the net impedance of this circuit should be equal to 0. So that will give rise to real part of Zin plus ZL is equal to 0 and imaginary of Zin and ZL should be equal to 0. So here I have labeled one of the impedances as Zin, other as ZL. So now if you look this Colpitts oscillator, then here we will label this portion as ZL, the impedance of series inductor, and R, which represents the loss of the inductor. And Zin, for Zin, we will take up the rest of the circuit. So this is going to be Zin. So what we find is Zin is basically the impedance of a part of Colpitts oscillator between this node, which is the gate, and this node, which is the drain of the MOS. So we can say that looking between these two nodes, what we see here is Zin. So our first task will be to find out this Zin. ZL is easy, straightforward. So we are now going to set up circuit for finding out Zin. So for that, we will substitute the MOS by its small signal model and include C1, C2 into it. So finding the Zin. So we have our MOS here. And then we have these two capacitors, C1 and C2. and between these two nodes, gate and drain, we want to know what is Z in. So for that, we connect voltage source, Vx, and find out how much current it is driving into this circuit. And once we know that Ix, we can find out the input impedance Z in as Vx by Ix. So here, once we take this current as Ix, this is also Ix. This source is grounded, of course. So this is Ix, and there is no current into the gate. So this current is equal to 0. So entire Ix takes path through C1. And then we will have a certain current here, I2. And then there will be another current I0 here flowing into the drain of the MOS. So now we are going to set up the equations for finding out Z in. So here we find that this Vx is basically equal to voltage of gate minus voltage of drain. So we have to find out these two voltages, Vg and Vd. So Vg is easy to find because we can see that entire Ix flows through C1, other end is grounded. So Vg is the voltage uh, developed by C1 because of Ix flowing through it. So Vg is equal to Ix into Xc1. And again, we are going to include the imaginary part into this X. Now for finding out Vd, we will have to set up equation KCL at this drain. So here we see that so here we find that Ix plus I0 is equal to I2. And this I0 at the MOS in gets splitted into two currents, IM and IR. So here we have Ix plus I0, which is IM plus IR is equal to I2. Now we can replace these currents. So IM is GM VGS, IR is current through R0, which is VO divided by R0, and I2 is current through capacitor. So this end is at VO, this is at 0 voltage. So I2 is minus VD. We will be calling it VD. VO is same as VD by XC2. And this VGS is actually equal to VG because the source is grounded. And in fact, this VO is also VD. So let us write it VD. So from here, we can now write this VA. We have already found out, sorry, VG. So this becomes GM into XC1 Ix plus Vd by R naught equal to minus Vd by Xe2. So here we can separate out Vd because this is what we want to know. So here we see that Ix into 1 plus Gm Xe1 is equal to minus Vd into 1 by R naught plus 1 by Xe2. So from here we find that Vd is equal to 1 plus Gm Xe1 at minus here Ix divided by 1 by R naught plus 1 by Xe2. So now we know the two voltages, both Vg and Vd. So we can now find out Vx. So Vx becomes Xe1 Ix plus 1 plus Gm Xe1 Ix divided by 1 by R naught plus 1 by Xe1. So now we will have to find out Zin. Therefore, Zin, which is Vx by Ix, can be found out as Xe1 plus 1 plus Gm Xe1, and denominator part we can write like this, Xe1 plus R naught. So numerator now contains R naught Xe1. And so now we know Zin, so we have to find out ZL, which is XL plus R. So these two things are known now, the two impedances. Therefore, from negative R model, what we find is Zin plus ZL is equal to 0. That means XL plus R. In fact, this is ZL. Now we can write Zin, which is Xe1 plus 1 plus Gm Xe1 Xe2 R0 divided by R0 plus Xe2. This whole thing is equal to 0. And let me point out that XL is J omega L. So we have to rearrange the terms by multiplying by this factor. And here we can collect Xe1 with this. So what we get is XL plus R plus Xe1 into R naught plus Xe2 plus 1 plus Gm Xe1 R0 Xe2 is equal to 0. So ultimate objective is to separate out the real and imaginary part. So what we will do is we will now expand this term. So here what we get is XL plus Xe1 into R naught. That means this term, and this we combine because this will give rise to imaginary part, and then this term and this one. So Xc2R. So here what we are going to get from this one is the imaginary parts, and real parts we can get as XL plus Xc1 multiplied by Xc2. That means this term, and this. And of course, this term and this term, that will also give rise to real. So here we have collected. And from the second term, we again get real and imaginary part. So real part we are going to write first, which is going to GM R naught. That means this one and product of this. And imaginary part is going to be R naught Xc2. So here we have this term and this term as imaginary part, and this one and this as real part. So we can now set up equation for imaginary part equal to 0. So when we equate the imaginary part, what we get is XL plus XC1 R naught plus XC2 R plus R naught is equal to 0. And this one will give rise to XL plus XC1 plus XC2 R0 plus XC2 R is equal to 0. So this is a general equation for the imaginary part of the equation 5. And here we can see that this one will lead to the lossless case. So we have arrived at this equation from the negative resistance model. But if we put for lossless case, R is going to be 0. So this will imply XL plus XC1 plus XC2 into R naught is equal to 0. So we have already encountered this equation when we analyze Colpitts for the lossless case using the feedback model. So we see that this one will ultimately give rise to the equation that we had already found out. That means omega square is equal to C1 plus C2 divided by L C1 and C2. So this is just to show that the negative resistance model analysis does give a result which is similar to what we had obtained for the feedback model. But we are actually carrying out the analysis for lossy case. So we'll proceed ahead with this equation that we have obtained here. So we get is XL plus XC1 plus XC2. This is already equal to 0. So we can substitute each of these terms by their expression. That means omega L minus J will cancel out from every term. So this is what we get for lossy case. Now here, so we have R naught omega L side, and then we can combine the rest of the terms together. So this gives rise to omega square is equal to 1 by L 1 by C1 plus 1 by C2 into R naught plus R by C2. So this omega square, then we will try to rewrite in terms of the oscillation frequency that we got for the lossless case. So we can take this factor outside. So here there will be R naught on this side also. So we have to divide it by R naught. So we have taken this factor outside. So this becomes 1 plus R by R naught into C1 by C1 plus C2. So here we see this is the oscillation frequency of lossless case. Where omega naught is so this is for lossless case. So therefore, for lossy case, the oscillation frequency is omega naught into 1 plus C1 by C1 plus C2 into R by R naught. And this is, of course, more than that of the lossy case, lossless case. And we can see that this will get reduced to that of the lossless case when R is set equal to 0. Now we are going to use the real part of the equation to find out what should be the transconductance. The real of equation 5 is equal to 0. This implies XL plus XC1 into XC2 plus R naught plus GM R naught XC1 is equal to, and XC2 is equal to 0. So this case also we can see that for lossless case, that means when R is equal to 0, what we get is XL plus XC1, XC2 plus GM R naught, XC1, XC2 is equal to 0. And we can replace this in terms of XC2. This will cancel out. So ultimately here also we are going to get GM R naught is equal to XC2 by XC1 is equal to C1 by C2. So what we have got here, this equation is a general case and can be easily adapted to lossless case also. So now we can elaborate this. So here, so we have to now replace this XL plus XE1 using the previous equation that we had got for imaginary. Here, the equation 6. So here we have this factor. So we can eliminate this factor from equation 6. So this is what we will get if we use those two equations. And here our goal is to find out GMR naught. So we get minus 1 plus R by R naught into XC2 by XC1 plus GMR naught R R0 divided by XC1 XC2. So therefore the intrinsic gain here is equal to 1 plus R by R naught XC2 XC1 minus R0 by XC1 XC2. So here in this case we find that intrinsic gain is unfortunately not independent of R naught, or in fact rather we will use this one to find out GM, which is going to be 1 plus R by R naught C1 by C2 into 1 by R naught minus R into C1 C2 and omega square. So here this will contain omega square as well, the operating frequency. So this is the transconductance required for the MOS at the oscillation. And this will become plus sign. Now if we look at the circuit, then this ZL has inductor and positive R. So it has positive reactance and positive R. That means the Zin must contain minus R and minus reactance. That means it should be of capacitive nature. So we can try to see whether this is the case. So for that case, so we can then find out the exact expression of the Zin by substituting these values of XE1 into this and separating out the real and imaginary part. So if we carry out that, So if we separate out the real and imaginary part for Z in, what we will get is like this: 1 minus Gm C2 by C1 into R0 divided by 1 by R0 plus omega square C2 square R0. So this is going to be the real part of this Z in, and imaginary part is going to be minus J into 1 by omega C1 plus omega C2 plus Gm by omega C1 R0 divided by 1 by R0 square plus omega square C2 square. So here we see that this imaginary part is clearly negative, implying this is of capacitive nature. And this real part, so real of Z in general will not be always negative, but it becomes negative for GMR0 C2 by C1 greater than 1. So this implies GMR0 greater than C1 by C2. So we had seen that this is the intrinsic gain of the MOS. So here we see that if it is greater than C1 by C2, this is going to be negative, and then only there will be oscillation. And it is not difficult to see that that is the case. Here we can see that R0 GM is basically this factor. So here we see that this is equal to C1 by C2 plus C1 by C2 R by R0 and R0 C1 C2 omega square. So this is indeed greater than C1 by C2. So for that case, this one will be negative and this will cancel out the negative R. So this will cancel the inductor, and this factor will cancel out positive R, which is the loss of the inductor. Okay. So we see that indeed that circuit behaves like minus R and capacitor for the oscillation frequency. We will now revisit the Colpitts oscillator for the lossless case, and we will point out one issue with that circuit. So here we have our Colpitts oscillator, lossless case. And for this case, we found the oscillation frequency to be equal to 1 by square root L C1 C2 divided by C1 plus C2. So this can be written as the ratio of C1 C2. and intrinsic gain was equal to C1 by C2. So when we try to design this circuit, we will have to uh, first say choose operating frequency. So for that case, we will be choosing L, and then we will be choosing C1, C2. So this operating frequency gets determined. But once you have chosen C1 and C2, this also becomes fixed. So we'll have no way of changing this GM or not. So there is a strong link between omega naught and the intrinsic gain of the oscillator or the MOS. So if we want to make this oscillator vary its oscillation frequency by changing capacitor, say one of the capacitor, then we see that we will invariably be changing GM uh, also. So if you want to make a tunable oscillator, it will be better that we have another parameter so that omega naught and the intrinsic gain or the GM can be sort of decoupled, and one will have a degree of freedom in deciding one of the parameters even when the first one is determined. So that leads to an oscillator called Clapp oscillator. So this is used to make tunable oscillator. So here we have a scenario quite similar to that of the Colpitts, except that we have one more capacitor in series with the inductor. So now we have a total of three capacitors, C1, C2, C3, and L. So here this is made variable when we want to change the oscillation frequency. Now for this case, we will try to find out what is the oscillation frequency and what is the intrinsic gain of the MOS required. So if we use the negative resistance model, then we can use the intermediate result of the previous analysis where we had a register here in place of C3. So if we try to go for the negative resistance model analysis, then now this L and C3, they form ZL, which is XL plus XC3. And the Zin is now formed by the same circuit that we had already analyzed. So there is no change in the Zin with respect to the previous circuit. So Zin remains same. So using the negative resistance model, so we still have Zin plus ZL is equal to 0. And Zin remains same. So we can substitute Zin that we had obtained here, this equation, and call it say 8. So this part we can use. So this is Z in, and then ZL is XL plus XC3. And this whole thing is equal to 0. So now if we compare this equation with the previous one that we had derived for the lossy case, then we find that in place of R, we have now this XC3. So that is where the difference occurs. So when we had the setup equation for the previous case, we can separate out the real and imaginary part here once again. So here we have for the real part R0 into XC1, and this is for the imaginary part, XC2 and XL. In fact, this R not multiplied with this whole thing, XC3. So this is going to give rise to imaginary part. And for the real part, we will have XC1, XC2, these two terms, plus GM R0 XC1, XC2, plus XC2 into XL plus XC3. So we see that X2 is common in each of the terms here. Here. So we now have this as the imaginary part and this as real part. So imaginary of this equation 9 equal to 0 implies XC1 plus XC2 plus XL plus XC3 is equal to 0. So here we have minus 1 by omega 1 by C1 plus 1 by C2 plus 1 by C3 plus omega L is equal to 0. So we find omega square is equal to 1 by L, and this becomes 1 by C1 plus 1 by C2 plus 1 by C3. So the oscillation frequency is square root of 1 by LC effective, but now C effective is going to be parallel of the series of C1, C2 and C3, and that will be equal to 1 by C1 plus 1 by C2 plus 1 by C3. So the formula for oscillation frequency is of similar structure as the case of the Colpitts, but now C3 is also present here. And here we can see that for large C1 and C2 with respect to C3, that means when C1 and C2 are significantly large compared with C3, then this C effective approximately becomes 1 by 1 by C3 is equal to C3. Therefore, the oscillation frequency is effectively equal to 1 by square root of L C3. So it becomes sort of independent of C1 and C2. Now let us see that what happens with the real part. So when we equate the real part, this factor should be equal to 0. So this is what we get, and now we can eliminate this part with the help of previous equation, this one, equation 10. So we can eliminate x1, xl, and x3 in terms of this xe2. From 10, we get minus xe2 plus gm or not xe1 is equal to 0. So this gives rise to well-known result, gm r naught is equal to c1 by C2, or in fact here it gives rise to x2 by xc2 by xc1. So we see that the intrinsic gain is independent of C3. And it depends only upon C1 and C2. So one can choose C1 and C2 to determine the intrinsic gain, and one can then choose C3 to find out the oscillation frequency. But of course, we will have to maintain this condition. So even in absence of this, we will have a degree of freedom in deciding the oscillation frequency by choosing C3, by changing C3, and GMR naught, it will remain totally unaffected, even when this condition is not fulfilled. So this is the advantage of Clapp oscillator, that it can be used to create the tunable oscillator.